Hi there, I'm Hugo Larochelle, and this is a presentation about meta-learning, an approach to tackle the problem of few-shot transfer learning. I originally gave this presentation at UBC Live, and after giving it, I was made aware that I had mistakenly overlooked some results that were quite relevant in the context of this research. And so I regretted the mistake, so I decided to go find the t-shirt that I had worn when I had filmed the original pre-recorded version of this talk, and just go fix the part where I could now discuss also these results in this presentation. And so I hope you enjoy, and let's get into it. But before we start, perhaps we could talk about transfer learning in general and why transfer learning is important. I got really interested in transfer learning essentially for the following reason. Noticing that deep learning was really successful at solving certain tasks when there was a lot of label training data for that task, I wondered about whether this was going to be the approach that would allow us to solve all the interesting problems we would like an AI system to solve. And as many other people, I think, one would realize that it's not necessarily realistic that we can expect for the full spectrum of tasks that hopefully an AI can solve that would collect tons and tons of labeled data individually for each problem. So practically speaking, it just doesn't seem like doing regular supervised learning within each individual task that we're interested in would be sufficient for solving all the problems we'd like to solve. And also at the heart of this difficulty, there's the observation that actually humans are, for certain tasks, pretty good at learning them from very small amount of experiences. An example would be recognizing visual concepts in images. We know that humans are really good at doing that from a small amount of examples or a small amount of experience. And so there seems to be this gap between the ability of humans to learn fast and the ability of machine learning systems right now requiring a lot of data, which is the equivalent of their experience, to learn a particular task. So closing that gap, I think, can be really interesting in understanding perhaps how humans we learn new tasks and also in achieving better performance in our system. And there's another reason for being interested in transfer learning, I think, is machine learning expert in general, which I got to through learning this, reading this paper, Shortcut Learning in Deep Neural Networks by these authors here, which was a really interesting kind of positioned paper that I really encourage you to go check out. It's about the notion of shortcut learning, which happens when a person or a system actually learns to solve a task, but not through the intended behavior, but by taking shortcuts. An example of that in humans might be that you would learn to solve or do well at an exam for a class, but not because you have a deep understanding of the topic, but more because you've learned shortcuts that typically occur in the types of exercises or questions that are being asked in the exam. And part of the idea there is that, and which is sort of explained in the paper, is that to avoid shortcut learning, looking at essentially what is the behavior of a learning system or even the person in other situations that are out of distribution compared to their learning experiences is probably key. And so in a sense, what I got from this paper anyways is that perhaps out of distribution evaluation is indeed absolutely crucial for us to be able to know and to develop systems that end up learning not shortcuts, but the intended learning behavior, which is essentially what humans have learned. And so I think a case can be made that really transfer learning, which is in the setting where we're looking at the performance in systems on a new distribution that is different from the one that most of training has been done, is perhaps really, really crucial for us to make meaningful progress in machine learning systems that develop the intended human behavior or intelligent behavior that we would like our systems to have. In this presentation, I'll focus on a particular type of transfer learning problem, which I call few-shot learning, or we call few-shot learning. So this is here an example of a few-shot learning problem, which is a 5-class, one-shot classification problem. In this presentation, I'll focus on image classification because it's easy to visualize, and it's also a task that intuitively we think that the system should be able to solve. So as I said, here we have 5 different classes, and for each class we have a single instance from that class, and that constitutes our training set for this classification task. And what we'd like in Fushot learning are machine learning systems that can take this small training set and make accurate predictions for the label of test examples and d-tests, so other inputs that have never been seen before, but that belong to one of these 5 classes. And so that's the problem of Fushot learning, and that's the problem that we'll be focusing on in this presentation. So for Fushot learning and transfer learning in general, one of the most successful approach that is being used right now is the so-called fine-tuning approach. It essentially constitutes in 2 steps. The first step is you take whatever large quantities of labeled data that you have for hopefully problems that are somewhat related to the task that you actually want to solve, the so-called target task. And then you will pre-train a model on that large quantity of data, usually some form of neural network. So that's the first step. And then the second step, the fine-tuning step, is just that you start from the weights of that neural network that you've pre-trained, and then you continue training, but now on a training set from the target task. And specifically in Fushot learning, the one sort of thing that characterizes a Fushot learning problem is that detrain, the training set for that target task, is going to be quite small. It's going to have very few examples per class. And that approach has been really successful. It's kind of the state of the art in many ways for transfer learning, the first thing that one ought to try if you're doing transfer learning. But one question as a researcher in machine learning, of course, is can we go beyond this? And this approach, in a sense, is kind of a recipe that we came up with, that we hand designed. And it's a recipe that uses as a subroutine training a neural net, because that's something that now we're really good at doing. We have really robust, solid tools for doing that. But ultimately, it's really kind of an arbitrary recipe. We pre-train and then we fine-tune, and there are a lot of hyperparameters behind this procedure. And so how might we be able to improve on that recipe? Well, one thing that we can do is think about the history of deep learning. And one of the motivations behind deep learning was to actually replace another recipe, which was to hand design some features and then apply some so-called shallow machine learning on top of those features. So the idea in deep learning was to say, well, let's have the full model represent both the classifier and the features on top of which we're classifying. So have the deep learning model learn the features and the task jointly, by providing a lot of examples of inputs and their corresponding targets. So one question we might ask is, can we improve on this recipe by trying to do the same thing, which is to try to learn parts of that recipe? And that's where meta-learning comes in. So in a sense, meta-learning here for Fushot learning is going to try to learn that learning algorithm, that is an algorithm that takes as input a training set for a task, and then gives us a way of predicting what will be the label y prime of any other new input x prime that might come from the test set of that task. And so we're trying to essentially design some neural network such that we can show it lots of examples of training sets for different tasks. And then what it will learn is to try to make good predictions for new inputs x prime of their label y prime. And then we're going to do gradient descent in that neural network. So in a sense, that's kind of a natural sort of transition from deep learning in the single task to a form of deep learning that tries to do end-to-end learning over multiple tasks. So that's sort of my perspective, or I like to present meta-learning. We're kind of taking a page from the deep learning book. We're going to try to learn instead of designing the learning algorithm that takes the training task and then gives us a way of making predictions to new examples by feeding it a lot of examples of tasks. And because we're learning a learning algorithm, we're calling that a learning to learn procedure, or we're calling that meta-learning. So going back to this problem where we have a 5-way one-shot classification problem, how would we train a system to be able to solve tasks like that? Well, as I said, we're going to try to train our model on lots of examples of tasks. So we're going to assume that we can construct a training set, or because each of in our training sets we're going to have multiple tasks, we're going to call that a meta training set, with each task having its own training set. And we're going to train our meta learning model on these meta training tasks. And once it's trained, we're going to evaluate our model on a meta test set of entirely different tasks. You might be wondering, how do we get these tasks? Well, we can get them, for instance, by when we do our research, by taking an existing data set, let's say ImageNet, and then we're going to take a subset of the classes that are in ImageNet, and we're only going to use them to construct tasks for meta training. And then we're going to use a different subset of classes to construct the tasks that are going to be used in the meta testing, or the generalization evaluation proportion of our experiments. And specifically, when we create tasks for meta training, we sort of sample these tasks one by one by taking all of the classes that we can use for meta training. We take a subset of these classes. In this illustration, we're always taking a subset of 5 classes. And then we sample detrain, a training set for that task, by sampling a single image from each class. And then we also sample more images from the same class, but different images, to construct the test for that task. And then we repeat that to be able to sample a lot of different tasks. And here, I should say, this is an example of a one-shot 5-way classification. But in Fushot learning, we might be interested in doing 2-shot, 3-shot, 5-shot, which would correspond to the number of examples per class. And later on, I'll talk about Meta-Dataset, which even considers classifying or performing experiments in tasks where there's a variable number of examples per class. And so when we do meta learning and we have this meta training set of tasks, the way we're going to be meta training is that we're going to go one task after another. We're going to feed detrain to our meta learner. And then our meta learner is going to be able to make predictions on the inputs in the test set. These are the X primes in my notation. And then we're going to have a loss that's going to compare the prediction with the true label that we can't use directly. We only use in the loss, the Y primes. And then we're going to do gradient descent, gradient of the loss with respect to the parameters in our meta learner, the model we're meta training, do one gradient descent step, and then move to the next task. And then we're going to do that essentially the same way that we're doing supervised learning, by having inputs that are in single image and then the label at the output. The only difference here, the main difference, is that the input is essentially the training set for a given task, and the target are the labels for subset of the test inputs that we want to make predictions for. So looking more deeply into the details, the kind of loss that we will use looks like this. So we will assume a probabilistic predictor over the labels Y prime of the inputs X prime that are in my test set of a given task. And then we're going to assume that our meta learner is giving us a distribution like this. So mathematically, we could write that as given some new input and given detrain, which is the training set for the task that we're asking the meta learner to make predictions for. So given that has been fed as input, give us a distribution over the label of this specific new input that I provided X prime. And so we usually have multiple inputs and target pairs in our d-tests. We'll just average, and here we're using essentially the negative log probability of the correct label, the cross entropy loss that we're used to in deep learning. And so many different meta learners or meta learning papers will suggest different ways of defining this conditional, this predictive distribution of the label of new examples given a training set for a task. So what I'll do now, I'll go over 2 really popular examples of meta-learning methods or models that define different predictive distributions like that. So a first example is the prototypical network. Conceptually, you can think of it as meta-training a classifier that's based on the concept of near-centroid classification, where when we get a new example, we're going to compare it with the average of the examples from each class, and based on the distance, we're going to try to classify it in the class that is closest to the average representation of that class. So mathematically, it's going to look something like this. The way that we're going to define the predictive label distribution for a new example x prime. So I should say here, next to x prime, there should be dtrain, but I didn't show it to be more concise. So the probability of the kth label, like the kth class, given this new example and dtrain, is going to be the exponential of the negative distance between some learned representation, f of x prime, so a learned representation of the new input. So the distance between that and what we call a prototype, or essentially the centroid of that class. That is, we're going to compute ck as the average learned representation for all of the inputs that belong to class k in my training set dtrain. That's what sk represents. It's all the examples in dtrain in class k. And so we're going to take the exponential of that and normalize by looking at the same term, but for all the classes. So in other words, we're feeding in a softmax the negative distance between the learned representation of x prime and various prototypes that we've computed, one for each class. And that's how we model this predictive distribution over the label of new examples from that same task. So one other way of thinking about this method, if we use as the distance the squared Euclidean distance, then we actually get the predictive probability of labels that we would get if we used a Gaussian classifier that is fitting a Gaussian per class and was using the same covariance, identity covariance matrix for all classes. So when we train, we're training this function f, this learned representation, which is going to be a neural network. So in the Gaussian classifier setting, you can think of this as I'm training my neural net to produce a representation such that doing Gaussian classification on top of it produces good results on the tasks that I see in my meta training set. That said, some people or some papers will use other types of distances, like the negative cosine distance is another one that is sometimes used. But I would still call that a prototypical network. Another way of thinking of the prototypical network is that we can think of it as a type of neural network where all of its hidden layers are the layers in that embedding function, that neural net that gives me a representation. So those would be the internal hidden layers of my model. And then I have an output layer that is taking this form, where instead of multiplying the last hidden layer by some weight vector, I'm taking that last hidden layer and then I'm comparing it with different prototypes and computing a softmax like this. So it's kind of like a regular neural net, but where the output weights or the output parameters are these prototypes and are computed thanks to the availability of a training set for that task. So that's prototypical network. You can read more about it in this paper here by Jake Snell and collaborators. Another really popular meta-learning method is model-agnostic meta-learning, or Mammal. So while the prototypical network, in a sense, was training a Gaussian or a representation that works well for Gaussian classification, or was trying to take inspiration from near-centroid classification, Mammal is taking inspiration directly from the fine-tuning procedure. Specifically, what it's going to try to do is to learn a good starting point to do some steps of fine-tuning on dtrain, the training set for a given task, such that it gives good predictions on the test example of that task. So its most common form is to assume that when we do fine-tuning, we actually use only one step of gradient descent. It's also the easiest to present, so I'm using that here. And so the predictive probability of y prime given x prime and dtrain is going to be the prediction of a neural net that is fed as input x prime, and essentially the softmax value that it assigns to the label, when its parameters are the initial parameters that we are going to meta train in Mammal, minus one step of gradient descent of those same initial parameters, but the gradient calculated on the training set of the task. So we're essentially saying, well, look at what are the predictions that I would make if I started from these parameters and then took one step of gradient descent on my training set for my task. And then let's look at what are the predictions now that I'm making on new examples that are in the test set. And because this whole formulation here is continuous, is differentiable, we can actually backpropagate into this predictive function directly into the initial value of the parameters, the theta here. And those are the parameters that are trained when we're training a mammal model. And so it might be surprising to think about using only one step of gradient descent. Two things about that. First, when we do Fushot learning, we have a very small training set. If we do many steps of gradient descent, it's not impossible we would start overfitting. So that's one reason why it might make sense. And actually, there are theoretical results from Chelsea Finn, the person behind this paper here, Mammal, and who later on developed various variations. And she also produced a paper which theoretically showed that actually, even with one step of gradient descent, we have some universal approximation. So a very flexible model of this predictive distribution under certain conditions. So we saw prototypical networks, we saw Mammal, and I will end by saying that we can actually combine the two with something that we call proto-Mammal, which is a variant that we proposed recently that we'll see later in this presentation. Proto-Mammal is essentially, instead of using learning just these parameters at the initialization, and if you think of this is a neural net that needs to have output weights. And you can try to train these sort of initial output weights. Oftentimes, you can also set them to 0. Well, instead, you can take inspiration from a prototypical network and actually use as the initial starting point of the output weights the prototypes that would be calculated by taking the initial initial representation of the examples in the training set and taking the per class average. So for more details on that, you can see our own paper where we describe that, where we'll see the citation for that a bit later in this presentation. Okay, so let's take a look at the performance we can get with prototypical networks and with Mammal, and we also see the combination of the two, proto-Mammal. We could do that on a benchmark that is extracted, as I mentioned, say just from ImageNet by creating tasks and separating classes between meta-training classes and meta-testing. However, in our own research recently, we suggested to try to go beyond that. Instead of focusing on a single data set, we propose to instead be in the multi-domain setting by actually creating tasks that are drawn from many different data sets, to try to push ourselves even more in the out-of-distribution evaluation. So specifically, we considered all of these 10 different data sets. And for each of these, we're going to separate classes. Some of the classes are going to be used for meta-training, some of them are going to be available for meta-validation, and some of them are going to be available for meta-testing. There's going to be one exception to that, which are the traffic signs in MS Coco. We actually, because they don't have that many classes, we're only going to use them for validation. We're not going to, or evaluation. We're not going to use them for meta training. So now what that means is that the pool of tasks that are potentially available in this benchmark comes from a variety of different sources and domain, which makes for a much richer set of experience that we can meta train a system. So we can look at the performance of various methods on Meta-Dataset. So the columns here correspond to different Fushot learning methods. It includes the Finetune baseline. It also includes prototypical network, and Mammal. FO is for the first order version of Mammal, which is a version where when we do gradient descent, we actually ignore the gradients, the second order gradients that come from taking the derivative through a gradient descent procedure. I'm not going to explain that too much, but I invite you to go look at the paper for more details. And we're going to look at the combination, proto-Mammal. So, and here what you have for each row is the performance for each domain on the test tasks. So for ImageNet, OmniGlot, aircraft, birds, texture, quick draw, fungi, VGG, flower, traffic signs in MS Cocoa, keeping in mind that for traffic signs in MS Cocoa, we don't actually have any training tasks. And also actually here in this particular table, I'm showing you the results where all the methods use only the data in the meta training tasks of ImageNet. So it's never seen OmniGlut or FCraft or BIRD's task before when evaluated. And the numbers you see here are essentially just the average classification accuracy on all of the task sample from all of these domains. And what you see at the last row is the average rank of each method for each, since it's kind of it's not really easy to compare the overall absolute accuracies between them. Using a ranking is an interesting different view on their relative performances. And so what we found is that actually combining prototypical network and Mammal, so a meta-learning method, actually did in general work better than, for instance, the common recipe of pre-training regularly and then fine-tuning on new tasks. So that's quite encouraging. It looks like the meta-learning method is able to improve on this recipe. That said, if you go look at the paper for more details, and I should say this is work led by Eleni Triantafilou, we also had experiments where we considered the setting where you could meta-train on all the training data available from all of the sources for which we have meta-training tasks. And in that setting, the results were a bit less encouraging. So we were not seeing as much of a difference in an advantage in using meta-learning. So that's kind of where this work that we did sort of left things off. There was a challenge in, so we have a new benchmark that looks at much broader out of distribution evaluation and training, but it looks like there is a challenge to be addressed when we meta-training from multiple domains. So since then, there's been a fair amount of research on trying to address that particular problem. And in particular, one of the state-of-the-art very recently is this paper from Dvornik, Schmidt, and Meral. It was just published at ECCV. And it's a method that relies on the concept of universal representations. Universal representations essentially, in short, refer to the idea that of trying to achieve a representation that is useful for any domain or for a large variety of domains. And one way this is, one simple instantiation of this idea is to, if you have, say, 3 different domains, unwritten character, bird species, and common objects, you would train with regular supervised learning separately a different embedding network or different backbone. So in this work, we often refer to these neural nets as backbones. So we're training different backbones separately on each domain. So each of these backbones is going to give us a vector representation of any given input image. And the way we're going to combine all of these backbones is by simply concatenating the representations that they're giving us, like so here. And in this paper, they present a method selecting universal representations that's motivated by the following idea. So this universal representation might contain all the information I need, but if I'm given a particular task with a small training set, well, maybe I actually don't want to look at or consider the representation from certain domains because it's actually not helpful for solving that task. So if I have a task that corresponds to categorizing different traffic signs, well, maybe I don't actually want to consider the representation provided from a backbone trained on unwritten character because it's a very different domain. And so in that paper, they don't use any meta-learning. They just provide a recipe for doing that selection of the different backbones. And that selection is represented by essentially multiplying each of the subvectors corresponding to each of the subdomain specific backbones by a weight between 0 and 1. So if you multiply by 0, effectively it's like you're not using that backbone from that domain. And so they provide a particular recipe, which is the solution of some optimization problem solved on the training set of the task for being able to select the backbones. And then that adjusted or adapted representation, F bar, is then used to perform nearest centroid classification. And so again, we can think about this progress. So they reported a really strong result on Meta-Dataset. So one question is, can we again improve on this recipe, and specifically the recipe they provided for selecting the most appropriate backbones for a given Fushot learning task based on its training set D-train? Can we try to improve on that recipe by using some meta-learning? So that's what we decided to do next in this paper here, a universal representation transformer layer for Fushot image classification. This was led by Lou Liu, and who's an intern at Mila, with me and Will Hamilton, another professor at Mila. And so the idea here is that we're going to not meta-train the backbones themselves. We're going to assume that they're available for performing Fushot learning. However, what we're going to meta-train is more the selection procedure of which of the backbones should I be using to construct a representation so that I can do something like nearest centroid classification. So specifically in our case, we're going to try to meta-learn some adapted representation that selects backbone F bar X, such that when we use that to perform in the context of a prototypical network, we're going to get good performance. And we're going to use the prototypical network training procedure based on training on many tasks using the predictive distribution of the labels that I showed before. We're going to use that essentially as the embedding network in a prototypical network and meta-train, as we do in a prototypical network, to backpropagate and train the parameters in this learned backbone selection mechanism. So the way we're going to represent the mechanism of choosing a backbone is going to be inspired from attention mechanisms like we have in transformer networks. So we'll start by assuming that we're selecting a single backbone from all the backbones that we have available. So that is, we're going to assume that f bar of x is the sum of all of the different backbone representation, the individual domain-specific backbones, but weighted by some alpha I, where the alphas sum to 1. And so if we train this and we reach a point where we have some saturation of the softmax that gives us these weights, then we'll effectively have a single weight of 1 on the backbone that we're effectively selecting for the task. And the way we're going to do this is as follows. We're going to use essentially the modules that's common in transformer networks, which is the scale dot product attention, where we have the notion of a query. And the query is conceptually going to be information about the task that we're going to get from the D-train, the training set of the task. And then the key conceptually is going to be the different backbones. And we're going to need to pick a way of representing these backbones for this problem. Specifically, the way that this scale.product attention is going to be used here is as follows. So let's take an example. Let's imagine that we have a two-way, two-shot classification problem. So we have two classes, waxcap and fly-agaric, and we have two images for each of these two classes. And let's imagine here that we have actually 4 pre-trained backbones that we can use. These are the 4 colors that you're seeing here. So in this method, the first thing that we'll do is that we'll apply the backbones, all 4 backbones on each of the images to get a universal representation for each of them, which is the concatenation of the output of each backbone for each image. And then we're going to compute the average. So we're going to do that per class. Because here the idea is that perhaps you want to select different backbones for each class. So f of S1, where S1 is meant to represent all of the inputs that are in class 1, f of S1 in my notation corresponds to the average universal representation of all of the images in class 1. And so f of S1 is going to be used as my query in my attention. This is what represents this particular task. And now I need to get a representation for each of the different backbones for that task. And simply what we'll use is what I note here as fi of s. For the first class, it would be fi of s1, which is just going to be the average of just the backbone fi, so over the class 1. So specifically, f1 of s1 would be just this first vector here. So that's the average over all the elements in my first class of the output of the first backbone. F2 of S1 is going to be the second, is illustrated here, the second vector here, and so on. So that's going to be each of these individual average representation that are backbone specific are going to be the representations of those backbone. And then I'm going to feed that through the typical scale.product attention module that we have in transformer networks, which has some parameters that is learning to essentially adjust the attention mechanism to produce particular attention scores or attention weights alphas. And I'm going to get these softmax weights, these alphas. There are 4 different alpha because there are 4 backbones. So I'm going to get per class attention weights. Then I'm going to average across all the classes in a way to sort of consolidate all of these preferences over backbones. And these are the alphas that I'm going to use to finally combine all of the backbones together and then recompute a adapted representation f bar x for all of my images in my training set, dtrain, as well as the images that are in dtest, in the test set of the task. And once we have that, we can compute the predictive distribution of the labels in the test set of the task from a prototypical network. We can compute a loss, and then we can backpropagate all the way into the attention mechanism itself so that our network learns to select the right backbone across many meta-training tasks. Okay, so that's essentially the method. However, in this setting, we restricted ourselves to retrieving a single backbone. But the way we can allow for retrieving multiple backbones is by simply having multiple attention heads and then concatenating the output of each of these heads. So essentially, in parallel, we're going to have more than one mechanism trying to, using attention, retrieve a specific backbone. And we're going to concatenate all of the selected backbone using this self-attention mechanism. In particular, in our experiment, when we cross-validate this hyperparameter of number of heads, we found that using 2 backbones is better than 1, and using more than 2, the performance more or less saturates. If you'd like more details about our method, you can go check out our paper on arXiv. You have the title here. And I should say that this work was led by my intern Lu Liu at Mila, and was also a collaboration with Professor Will Hamilton at Mila. So let's look at some results on Meta-Dataset, but where we allow methods to meta-train on all of the training data from all of the different data set sources for which meta-training data is available. Actually, if you've seen this presentation before, you might notice that this part is slightly different. So after I've given this presentation before, I was made aware that I had mistakenly overlooked some results that were also published at CVPR for this method called Simple Synapse, which actually was doing really well on Meta-Dataset as well. So you have the reference here if you want to go check it out, Improve Fushot Visual Classification. This is from UBC, from Frank Wood and Leonid Segal's group with PhD students Peyman Bateni, Raghav Goyal, and Vaden Masrani. And so now looking at the results, first if you focus on comparing directly SIR and URT, since URT builds on SIR using the same backbones, generally what we find is that URT never does worse, statistically worse than SIR, and actually improves on 4 different domains. On Omniglot it improves, on birds, on QuickDraw it improves, and also on VGG flower. And then if we actually look at, for each domain, for each data set source, which method is actually performing best, statistically best. So for any given domain, you might have more than one bolded entry because the confidence intervals overlap, and so we consider them equivalent. But if we look at the number of times that each method is first, actually URT does really well here with being first on 7 different domains. Whereas the other methods, Simple Synapse is first on 3 domains, and then SIR is first on 4 domains. So it seems like by combining some notion of meta-learning and using this notion of pre-trained backbones, we've been able to improve further on SIR and get better results. Some work also has looked at evaluating on other data sets that aren't in Meta-Dataset, specifically MNIST, CFAR10, and CFAR100. And so we also reported numbers for these. Here, notice that these are domains that, much like the 2 domains here, traffic signs and MS COCO, we actually don't have any meta-training data available on which URT or SIR were meta-trained. and or any of these other methods. And so it turns out that URT there does neither worse nor better than SIR. On the MNIST domain, SIR and URT are best, whereas on the CFAR10, CFAR100 domain, Simple Synapse has the best performance. And so what we're seeing here is that there seems to be a challenge for meta-learning methods and few-shot learning methods in general to kind of robustly do better in a more truly out-of-domain generalization setting. So within domain, but different classes, so it's out-of-distribution generalization on these 8 domains here. However, it's still sort of within the same domain because this is the same original source data set. It looks like meta-training has helped, at least in the case of URT, achieving better results. But for the truly out-of-domain setting, which would be traffic science, MS COCO, and these other domains here, it looks like there's still a challenge at achieving robust improvement, which I think is an interesting challenge for future few-shot learning research. We can also visualize what do these attention heads do? What did they learn to do when they are faced with different tasks from different domains? So we're seeing that in these 2 tables here. Each table corresponds to one head. And for each head, what we're doing is that for each row, we have a particular domain that gives us tasks for evaluation. And on the column, we have different backbones, which also labeled by a data set because the domains correspond to different data sets. And what we do is that we take the average alphas, the average attention weights that are provided by each head over all of the tasks from each of these domains for evaluation. And what we're seeing is something interesting. This head here has learned for all of the domains for which we have meta-training tasks to actually find the correct backbone from the same domain. This is why on the diagonal we have really large attention. Also for the 2 domains that were truly out of domain in the sense that we didn't have meta-training tasks for them, instead it decided to rely a bit more on ImageNet and then sort of mix some of the other backbones. And then the other head actually did something complementary to the head that selected the domain-specific backbone. We have some interesting things where we see that for Omniglot, while one of the head was able to find the backbone specific for Omniglot, it also decided to use QuickDraw as the other backbone, where QuickDraw is also handwritten or drawn symbols and characters. I think it's only symbols and objects. And we have sort of similar kind of behaviors here that make quite a bit of sense. So it is interesting to see that with meta-learning, it was able to learn a strategy that seems rational and makes sense. So I'll stop here and perhaps with a few words on what I think are the remaining challenges. So with this last work on URT and on combining pre-trained backbones with some meta-learning, I think there's maybe a combination here that for the future is perhaps the right way of trying to improve on end design recipes. We can think of pre-training as being a really convenient way of acquiring knowledge from many different domains. And then perhaps meta-learning can be thought of as what's the reasoning component of solving this task? How do I combine this knowledge that I've acquired in a way that I'm able to solve new problems or new tasks? And I think there are many other things that could have been done. This example with URT is in a way a relatively simple one, and I'm sure that we can design improved versions of a similar idea. I think we also should strive towards continuing to improve our benchmarks like we did with Meta-Dataset. Hopefully Meta-Dataset will continue to be useful to evaluate this much stronger, more difficult out-of-distribution evaluation in multi-domain setting. But I think that the more domains, for instance, that we can add to a future benchmark, I think the better. Definitely for meta-training, but also for just evaluation purposes. So I think we need to continue to do that. We should also better understand the impact of how we're sampling tasks. So I've not really described that problematic much, but the way we sample tasks, there's a few choices that need to be made. When I sample tasks for meta-training, how many classes do I pick? Or what's the distribution of number of classes that I consider? what is the number of images per class, and how imbalanced do I want to make these particular tasks be. In Meta-Dataset, we try to sort of use a large variety of number of classes and a number of examples per class with the intention to be able to evaluate performance across many different regimes. But it's quite possible for meta training that there is actually a curriculum on how we sample these tasks that would actually make meta learning much more effective and produce better systems for Fushot classification. So I think this is something that we've barely scratched the surface of and would be interesting future direction. And also I think and this is perhaps a bit more of an engineering question, we should really work on improving the scalability of our meta learning methods. I think one of the key reasons why fine-tuning remains a really useful and effective method for transfer learning and even few-shot learning is that it relies on a really robust set of technologies and software for training neural networks. And the technology, the tooling is much less mature in meta learning. So I think there's definitely a lot of room for improvement there, and that might very much help us explore even more this interface between, I guess, regular deep learning and supervised learning and approaches that are based on this notion of meta learning. So that's it for me. Thank you for your attention.